All right, hi everyone. Today this lecture is about giving you an overview on trustworthy machine learning, which has become a really popular topic in machine learning these days. So here's the outline for today. First, we're going to talk about out-of-distribution reliability. So there are in total 3 subtopics in this realm of trustworthy machine learning. And this is the first topic we'll dive into today. And the second is about adversarial robustness. And thirdly, we'll look at fairness and group robustness. So let's first dive into this reliability against out-of-distribution data, which is the research topic that I'm personally also very excited about. So to motivate this problem, here I want to use this example back from the first lecture, if you remember. So let's see, imagine you're trying to develop this phone app, which can automatically classify images of food so that you can show users some recipes or nutrition ingredients. And to do so, typically the workflow involves, collect some training data and annotate those images. And then you can take any of your favorite neural classifier, which we have already covered extensively in the very first few lectures and paper presentations. And once this network is trained, and you can go ahead and then deploy this model in this real world. And in order for this model to work well, right, we have to assume that users would only upload photos that would look like your training data, which are the images of photos. And as you have already know, that this is the classic closed word setting where we assume the training and test data distributions to match each other. And the reality rarely holds, and we would anticipate in a lot of these applications that the test data might very likely to differ from your training. And so, for example, this could be any data that users would upload to your platform that is outside your training domain. And the interesting question here is, how can we build machine learning models that function reliably in such an open world environment? And so, for example, when a bird image comes into your food classifier, ideally you should flag this photo to be out of distribution because it has nothing to do with those categories of food, right? And this out-of-distribution uncertainty or reliability is also very important for those safety-critical applications, such as identifying COVID from regular pneumonia based on this chest X-ray scans, or in autonomous driving, identify these unusual objects on the road, right? So these are some of the common examples. And so let's walk through use simple example. I'll be using this running example, let's say a traffic sign classification, to explain this problem setting. So you can take this traffic sign training data set and train on your favorite neural network. And here we use softmax to denote the probability for this image to belong to each class. And this is a vector that sums up to 1. And we define this softmax confidence to be the maximum probability among all these classes. So when the network converges, it would produce a very high confidence score for those traffic sign images, for example, 0.99. And this is not surprising because the neural network is typically trained on this cross entropy loss, right? This is one of the most common loss that you probably seen in reading these papers. And naturally, this cross entropy loss would amplify. And why is that? Because let's consider a softmax, which is the predicted output that produced 0.8 for this class and 0.2 for the other one. And this is the true ground truth label. So cross entropy loss basically tries to calculate this negative of log likelihood for the probability that corresponds to the ground truth label, in this case, 0.8. And as you can see, in order to minimize this cross entropy loss, essentially you want to push this probability to be even higher, right? So if it's somewhere closer to 1, this loss would effectively reduce down to log 1, which is 0. So essentially the goal is to push these two vectors to be almost identical in order to minimize this. And so this explains why we're observing this high confidence on those in distribution or training data. However, there could be a problem during test time. Let's say when there is a completely irrelevant image such as a mailbox goes through the same network trained on traffic signs. And ideally, we would hope this produce some, low confidence because it has nothing to do with those traffic sign labels. But in reality, this still produce a moderately high confidence score. And this mailbox image comes from a data distribution that is outside our training distribution. We call this out of distribution example or OD example. And turns out neural networks can be quite overconfident to these out of distribution examples. And this is what researchers have previously verified extensively on a lot of this modern neural network architectures. And to see this is indeed the case, let's take some examples, right, that are sampled from in distribution, which is traffic sign distribution. And then we calculate this softmax confidence score for each of those. And similarly, we do so for a bunch of out of distribution images and then calculate their softmax score. And if we plot those confidence scores at a population level, this is what this distribution looks like. So this green curve indicates the aggregate confidence for the in distribution. And this gray curve indicates that for the out of distribution. And as you can see from this curve, they tend to overlap a lot, right? So it's non-trivial just to separate out in versus out of distribution by drawing, a threshold somewhere. And the question becomes, how can we distinguish out of distribution examples from those, training distribution in this modern context of deep learning? So these are some of the popular methods that came out in recent years. And broadly speaking, we can classify those approaches into two categories. In one category, we use this pre-trained neural network but having to modify these parameters. And this could be very convenient, especially considering this realistic situations when you're taking a model in deployment and you don't want to change kind of the existing kind of model at all. So essentially, the goal is to derive some reliable statistics, such as indicator scores, which we can rely on to kind of differentiate between in distribution examples versus out of distribution examples, right? So that's kind of the common idea of these approaches, and we'll be diving into some of those shortly after. And in another category, we're making a slightly stronger assumption to say, what if we're allowed to retrain or fine-tune this deployed model? So the parameters might as well change, but we might get kind of stronger reliability just because we can regularize the model in a better way to defend against those out-of-distribution examples. So in fact, one of the very first paper on this topic that we'll see next week fall into this category. So I'll first talk about this method called Odin, which is in short for out-of-distribution image detector. And this is the paper we published back in 2018, and now it has become one of the most popular techniques in out-of-distribution detection. So to see how this method works, this technique comprised of essentially two components. The first component is called temperature scaling, which was a technique invented by Hendon et al. That was used originally for knowledge distillation. So this is essentially very simple. So recall this is how softmax was calculated before, right? And if we're applying temperature scaling, essentially we're dividing this original output vector f of x by a constant t, and t here is called temperature. And then we calculate the softmax the usual way, which is essentially taking the exponential over these, scaled output and then normalized accordingly. So temperature scaling has two interesting effects here. The first is that it would push all of these confidence or confidence scores to be somewhere closer to 1 over n. And here n is the total number of classes. So let's say if you have 10 different output classes, this would essentially push the score closer to be somewhere close to 0.1. And this is, we said it's mathematically, we can show this. And the second effect, which is more important in this context of OOD detection, is that it makes these two distributions make this blue, the green versus gray curve more separable. And to see why this is the case, we can approximate this confidence, which is P of y hat, and y hat indicate this probability that corresponds to the largest output using Taylor approximation. And here you can see that when this temperature T is sufficiently large, this term is mostly dominated by this first order term. So what this first order essentially measures is on average, how this largest output among all the classes f of y hat deviates from the remaining outputs. And so if we were to measure this empirically, this is one example that we're taking a neural network that is trained on CIFAR10 in red curve here, right? So this is essentially the in distribution data. And this on x-axis, we're measuring this first order term. And as you can see, in distribution data tends to have this larger kind of deviation on average. And for all of these other curves, we're plotting this for some of the out of distribution data sets that we consider. And as you can see, there's a strong separation in between these two. So that explains, why we're observing this stronger kind of separability. And the second component to Odin is called input processing. So if you're familiar with how adversarial examples are constructed, which is okay because we'll, if you're not familiar, we'll get to in the second part of this lecture. So essentially, we're taking an input image and pass that through this neural network, right? And we get this kind of loss function, and then we calculate gradient with respect to this loss function. So we're taking this input image, and we subtract this noise with magnitude epsilon, depending on the sign of this gradient that we just calculated with respect to this loss function. And this is a slightly perturbed kind of out of distribution image. And essentially what this perturbation does is to push, this confidence to be even higher than where it was before, right? So that's why we're subtracting this noise, depending on the sign. Okay, so interestingly, as I said, it would push this confidence to be higher than it was before. But even more interesting, kind of the subtlety here is that the increment for the in distribution here, so the gap between these two green curves is more significant than the gap between the two gray curves. So this results in actually stronger separability between these two distributions, which makes them further kind of separable. And I won't go into the technical details because it would take some time to actually explain. So putting all of these two components together, let's say we have a pre-trained classifier in order to classify this traffic sign data, and they wanted to build this out of distribution detector G of X. These are two different classifiers. And green is out of distribution, and the circles are in distribution. So what we do is to perturb this image using input preprocessing technique, and then calculate this calibrated softmax score using temperature scaling. And then here we compare, and during inference time, compare with this threshold delta. If it's smaller than this threshold, we consider that to be out of distribution. And if it's greater than delta, we consider that to be an in distribution. And this delta in practice can be chosen so that the true positive rate, let's say the probability of classifying this to be correctly as in distribution is 95%. So the advantage of this method is that it doesn't require, modifying the neural network parameters at all. So this classification accuracy on this original task, which is traffic sign classification, is retained. And let's see how this actually works in a situated example. Let's now take, inference time. When a new example comes in, we first pass this through this detector G of X. And if that's, identified as in distribution, we then kind of pass that through the downstream classify f of X. Otherwise, we flag those as out of distribution. So to evaluate this approach, we take a pre-trained neural network using dense net architecture, and now you're seeing, how this actual architecture actually works, right? So we do this pre-training on CIFAR10 as in distribution, and then we evaluate this network using a subset of ImageNet data as out of distribution. So this is the same network that we just trained. And here's what the results look like. So this red curve is when we're using this kind of raw softmax confidence. And this blue curve is when we're using Odin as a detection. So as you can see, when this true positive rate is 95%, which means 95% of CIFAR10 test images are correctly classified by this detector. And this false positive rate is reduced significantly from 34.7 down to 4.3, which is quite substantial. And we verified this thoroughly on more data sets. These are all the different out of distribution data sets that we considered back then. And the performance improvement in terms of false positive rate is quite substantial. So this green bars are for Odin, and the blue bars are the baseline method. So ever since then, there has been, a lot of exciting progress that happened in this domain, and a lot more work was published on this important issue of out of distribution detection. So this is another work that I want to briefly highlight here, which is based on this notion of Mahalanobis distance. And this was a paper published at NeurIPS 2018. So the idea is essentially to try to approximate each class as a multivariate Gaussian. So for example, here we're having two different classes for cats versus dog, and you can try to essentially approximate using a Gaussian for each of those, blue and gray. And in order to estimate this distribution, essentially what this method did is to take this pre-trained neural network and then extract these features from intermediate layer or the last layer, and then basically estimate the mean and covariant matrix from this extracted features. And then during inference time, they use this distance with respect to this closest class, which is also known as Mahalanobis distance, to detect out of distribution. So the intuition here is, if an image is belonging to your training or in distribution, for example, if you're having a different dog picture, this distance should be somewhere relatively small. Whereas if we have an out of distribution image, in this case, a mailbox image, it's going to be far away from, the mean of all these classes. So this essentially is the criterion that they use to detect out of distribution data. And this is a recent kind of a latest work that a student and I have recently kind of worked on. I'm personally very excited about this work because I think finally this field is heading somewhere. We're able to kind of derive certain statistics from a pre-trained neural network that can be explained in a more principled way, right? So to see kind of this energy-based out of distribution detection, let me first explain what energy-based model essentially is doing. So this is something has been around in physics long time ago, and Jan LeCun has this really nice tutorial that was published in 2006 on energy-based model. So to briefly explain what this means, let's say we take any input data that belongs to this RD space with corresponding label Y, which is a cat. And then this goes through an energy function, which produce an energy value which is scalar. So essentially, energy function tries to produce, a low value energy for the observed data points and relatively high energy for unobserved points. So because energy is actually non-probabilistic, because it's a free range value, can be anywhere. So in principle, you could turn this into probability density through the Gibbs distribution. So here P of y conditioned on this x could be calculated by taking this exponential of E of negative energy, and then this normalized term is basically integrating over all the possible classes. So this is the same equation that we just saw earlier, and we call this partition function. So you actually equalize this to partition function. You could actually denote, express this we call free energy. This is a classic term that already exists in physics for a long time. E of x in terms of this kind of partition function. So minus T is the temperature, you already seen this, multiplies with this log likelihood of this partition function. So you might be wondering, how does that connect to this setting of neural networks that we're talking about? So it turns out neural classifier can be implicitly interpreted from an energy-based point of view, right? So let's consider a neural network that is pre-trained on certain task and then produce output f of x, and this network is parameterized by theta. So we have class output F1, F2, all the way to Fy. And after softmax, is produce basically this condition probability, P of Y condition on your input. And this is, you're familiar with, how softmax is defined, right? Essentially taking the exponential over all those different logits, normalized by the sum of exponential. So it turns out, if we define this energy, right, for any pair of input and output to be this negative of the logit, this suddenly becomes the form, right, that looks familiar from the slides previously, which is the energy-based model. And so in this context of deep networks, we can define this free energy to be the negative of this log sum. I'll actually show you. So this is, previously how it was defined. Here in this context, neural networks, essentially we can replace this integral with a summation over different classes from 1 to k, which would look like this. And this is exactly this log sum EXP operator that I'm talking about. So it can be calculated in a very convenient way given any pre-trained neural network. So now what we're proposing here is to say, now instead of calculating the softmax score, which suffers from this overconfidence issue that we already seen before, we wanted to calculate instead this energy function from any pre-trained neural network. And this energy function has this really appealing property that would kind of avoid producing this overconfident distribution in this, if you measure the statistics in terms of the energy here. And let me explain why that is the case. I think this is kind of my favorite part of this work, is we're able to show this theoretical motivation. So it turns out we can express the density function for your training data. Let's say P of X, right? X can be think of as sampled from your training data in terms of this notion of energy. And this, basically this denominator takes this integral over this entire input space, which often can be intractable to compute, especially when you have an extremely large sample space. You can't even estimate this term tractably. But the nice thing about using this kind of probability density is that we don't have to actually calculate this, because it's going to be the same, right? It's sample independent. This term is going to be shared regardless of what sample that you're taking from your in-distribution data. So we could actually ignore this for the purpose of out-of-distribution detection. And so here, it turns out this density is proportional to this exponential of this negative energy. And through the simple derivation, you can see that the energy is proportional to this log likelihood of your training data. And this explains, why energy is better suited kind of measurement for this kind of task. And even better, you don't even have to explicitly estimate this density using, GAN or VE or density estimation, other density estimation techniques. It can be very effectively derived just from a pre-trained network using the standard supervised learning techniques. And in contrast, now we're also able to actually explain why softmax is the wrong metric to look at, because effectively it doesn't align with this probability density of our training data. So to see this is the case, this is how maximum softmax score is derived. We're taking this max among all this probability output, y condition on x. And effectively, this can be, redenoted in this form. So here we're using this fmx to denote this logit that corresponds to the largest output. And through the simple derivation, we can see that MSP is proportional to this energy shifted by this maximum logit term, right? So therefore, it's actually, because energy is proportional to this term that we just saw, which makes softmax actually in proportional to this density function here, right? So this is why we're observing this kind of very skewed distribution earlier on. So these are some comparisons in terms of evaluation that we performed on CIFAR 10, which is the in distribution, and CIFAR 100. And energy-based approach is able to consistently outperform this previous method. And even nicer, this is actually a parameter-free approach that you don't have to perform any hyperparameter tuning stuff. So this is certainly nice. And another work that I want to also mention is a recent work also in collaboration with folks here in UW-Madison called Adversarial Training with Informative Outlier Mining. And we're going to have a paper deep dive next week on this paper. So I just wanted to kind of briefly explain this intuition here, just to set some context for this work. So recall, I've talked a lot about approaches that rely on this pre-trained neural networks where we're not allowed to kind of change the parameters. But as I said earlier, if we can make some slightly assumption and if we're allowed to change this parameter, we can actually get models that have stronger kind of regularization effect to improve this out of distribution detection performance. And this is exactly, the kind of the category where this work falls into. So the idea is to see if we're allowed to take some auxiliary data used as a surrogate, as OOD training data, so we can get better estimation on this decision boundary between here your in distribution and out of distribution, which is in gray here, right? So that's kind of the idea, the general idea behind this entire line of approach, that you want to regularize your model. So it can kind of draw some circle near this in distribution data. And a core kind of message that we wanted to show in this paper is that it's actually very critical, like in terms of when you're training with this auxiliary data or unlabeled data, how you select samples from those. If we're just blindly sample uniformly from this entire kind of auxiliary data distribution, you might get a kind of a loose decision boundary that is not very robust. And in contrast, if we can do this kind of more in a more selective way and only select those out of distribution samples that is somewhat close to your in distribution but not quite, we can end up getting a much tighter decision boundary. And it turns out to be much, much more robust than the previous estimation that we get. So this is kind of the high-level overview, and we will learn more about some of the specific training techniques as well as the evaluations that we bring into this work in next week. Abhirav, you have a question? Do you want to speak up or?
Yeah, Professor, when you say out of order distribution, how is that determined exactly?
That's a really great question. So I think one way to think about defining out of distribution is using this very classic statistical notion. For example, if you read this Odin paper, there we try to measure this notion of out of distribution using this distribution distance called maximum mean discrepancy. So effectively, you can, think of relying on the scale divergence or maximum mean discrepancy to measure the difference between your distribution versus out of distribution. And for evaluation purposes, we typically take data sets that is, let's say, have semantic classes that are sufficiently different from your training data. So that's kind of a proxy for evaluation purposes. But if we want to define this more in a more principled way, there are, very classic statistical measurement that allows us to do so. That's a really great question. Harit, you have a question?
Yeah. I was curious to know whether there could be any fairness issues if we do auto-distribution detection. So, for example, if you are making an app for face recognition or anything to do with people, then in that case, suppose there are some, let's say, a different class of people, maybe with different ethnicity or maybe color, but then your classifier says that this data is out of distribution.
Absolutely. This is, in fact, one of the ideas I was actually talking with one of my students the other day. So this bias or fairness issue can certainly arise in this out of distribution detection setting. And that's, in fact, an underexplored aspect, because often we were training this or estimating this decision boundary, we're kind of taking it for granted that these data samples are sampled uniformly and is representative enough kind of for this overall training distribution. But as you said, it might very be likely that the training data that we use for out of distribution detection estimation, can be biased, and you end up having this very biased decision boundary. So that's something I think would be very, very interesting, but hasn't been explored in the field. Very great question.
Okay, thank you.
Thanks for that. Any other questions before we move on? Let me see the next slides. I like all these questions that you guys are raising. So that's kind of the overview on the very first subtopic of out of distribution reliability, and I also wanted to use the rest of the time to give you guys some overview on the other two topics, which I also think is important. So let's look at adversarial robustness here. So for those of you who are not familiar with adversarial examples, this is one nation I pulled from this OpenAI blog. So essentially, these are inputs to machine learning models that an attacker has intentionally designed to cause the model to make a mistake. So this is the classic example that you've probably seen in a lot of presentations, where this photo of a panda is slightly perturbed to produce a prediction of a gibbon. Right? So these are some of the early papers that we should credit to that point out this, this interesting phenomenon of adversarial examples. And it turns out adversarial examples could exist not just for neural networks. You could actually create adversarial examples for linear models as well, and logistic regression, softmax regression, SVM, and so on. And so to see an example here, this is when we're taking a linear model trained on ImageNet, and we'll try to add this perturbation, which is shown in this middle panel here. And then the original prediction is goldfish, but now it becomes 12.5% of daisy, which is an adversarial example with respect to this linear model. And adversarial examples could also occur in natural language processing. So this is a paper by Percy group published in 2017. And here, this blue text essentially, this, you can think this perturbation that you're adding to this original corpus here. Quarterback Jeff Dean, blah, blah, blah. And then if you ask this question, the original prediction should have been John Elway, and now it's, kind of changed to this Jeff Dean, which is, out of this specific context. And it turns out adversarial examples could even exist in the physical world as well. So to see, I think a straightforward way is to actually show you guys this video if you haven't seen this, right? So let's see if this video would work. Let's try to click on. You guys see the video now or not really? So here they're taking this turtle and adding some, artifact here. And so you can see these bars are the real-time predictions, right? It's overshooting on this rifle class. Okay, that's it. So how can I exit this and go back to the slides? So you might be, wondering how we can generate those adversarial examples for a machine learning model. So this one really simple and kind of a classic approach is called fast gradient sign method, FGSM. And if you read this ML related papers, you will see this method quite extensively. So here, effectively, we're taking an original input, X, and this is the perturbed image, X tilde. And we're trying to essentially search within this neighborhood of epsilon ball surrounded this input, right? So you're searching when this LP norm is constrained within this epsilon ball, and you're trying to add this perturbation so that essentially you just perform one step of gradient. You're adding this gradient of magnitude, right, epsilon, depending on the sign of this gradient. So you probably would, hear some other techniques like PGD. Essentially, that's like an iterative method which performs more steps so that you can create an even stronger attack. And in order to defend those adversarial examples, this adversarial training has, proven to be one of the effective techniques. Just briefly explain how it works. And again, we'll have deep dive on this in one of this paper presentation. So at a high level, this is the original training data that we're using to train this neural network, let's say BERT. And now in this adversarial training optimization, we're trying to intentionally, create some of these worst case adversarial perturbations like this. And then we still want this model kind of to predict this image to be BERT on these adversarial examples. So overall, this optimization can be thought of as a min-max game. Whereas inside this loop, you have a max which try to create adversaries, right? It's creating this worst possible adversarial images, and then the outer loop still tries to minimize this loss on top of these perturbed examples. And effectively, adversarial training can be viewed as, augmenting your training data with these adversarial examples that are generated on the fly during this optimization process. So that's, a way to kind of connect this training technique with augmentation techniques. So here's a training curve that I want to show you guys on this effectiveness. So most importantly, let's first look at this curve, this green curve on the very top here. This is when we're training on the clean images and evaluate on adversarial perturbed image. And what you're saying here, basically, all of these test examples basically fail, catastrophically, and the classifier is not getting most of them right. And in contrast, this light green curve is after applying adversarial training, and then evaluate again on adversarial training, right? So now you can see that this test error rate is much, much lower, which indicates this effectiveness of adversarial training technique. So you might be wondering, why machine learning models are prone to adversary. And there has been a lot of kind of conjectures in the field try to, demystify this. And here I'm just, listing a few kind of popular common belief here. The first conjecture is overfitting. So remember, we're dealing with a very over-parameterized a model here in this modern setting of neural networks. And you can imagine you might end up fitting a function that can be an arbitrary shape because you have so much parameters to disposal. And here, this decision boundary, you might end up having a decision boundary, that's kind of well carved around your training data. And what that means is these images that are correctly kind of classified are also sufficiently close to this decision boundary, which means if you add any slight perturbation, they're likely to go outside your weird kind of decision boundary you end up fitting here. So that's, one conjecture. And the second conjecture is due to this excessive linearity. And remember, in the very first lecture, I kind of showed you guys about this ReLU function, rectified linear unit, which is taking the max between your input and 0, right? So that's the most popular activation function used in a lot of these neural networks today. And you end up having a decision boundary, right, for these models that are near piecewise linear because of this excessive adoption of linear ReLU function. And it turns out in high-dimensional space, this linear hyperplane is prone to perturbation. So that's another kind of conjecture for this phenomenon. And third conjecture, from a data perspective, it could be that your data has very small interclass distances. So for example, if you take MNIST, the class 1 and 7 look, very similar, and so is 3 and 8. So when this interclass distance is small, it's kind of easy to change them around to make it closer to the other the class. So that's kind of the conjectures there. And I also wanted to point out this interesting paper called Adversarial Examples Are Not Bugs. They're features by Alexander Madre's group. And so what this paper is trying to, bring to the table is, is another kind of conjecture. Can we say conjecture 1 is very similar to conjecture 3? So yes, they're related, but you can think this from different perspectives. So conjecture 1 basically is saying from this decision boundary, right, from this model perspective, that you end up having this decision boundary that's overfitting to your training data. And conjecture 3, in contrast, is trying to look at things from the data perspective. So model versus data, they are related because often you have these two go hand in hand. Great question. Okay, so coming back to this paper here. Okay, awesome. this paper essentially is trying to bring this an interesting conjecture, which is, adversarial examples can be directly attributed to this presence of non-robust features, which means features derived from patterns in the data distribution that are highly predictive yet brittle and incomprehensible to humans. And so to give an example here, this is the figure taken out from this paper. Basically, we have this training example, which is a frog, and these are the data set with robust features and versus non-robust data set, which is look like this adversarial kind of perturbation patterns that we've seen. And if you train on those non-robust data set, you end up getting good accuracy on your clean data set, but terrible accuracy on these perturbed images, which means robust accuracy is low. And in contrast, if you train your model using robust feature, you end up getting kind of good accuracy on both tasks. And so if you recall this adversarial training technique that we were talking about earlier, right? It's actually why it's effective, because it's helping the neural network to learn these robust features. So for example, if you take this original image and the robust feature should have been associated with this labeled dog, and during this optimization, right, this would create some adversarial example that perturb this dog to be predicted as a cat. And here, essentially you're adding some of these non-robust features to your training data set. And that's essentially, trying to inject this non-robust features. And so that encourages your network to pick up on those robust features in order to actually, learn reliably. So I think we have about, I want to wrap up in the rest of 10 minutes. I think we should be able to finish this lecture on time. We have another subtopic, which is the third one. I also wanted to overview here, so to provide some context before our paper presentation starts. So in the past few years, we've seen kind of a exponential increase in terms of interest in this fairness domain, and Hurd actually pointed out this, this aspect in an out-of-distribution setting as well, right? So you see a lot of papers that are being published every year now. I think this number is even higher because this last year was 2017. I haven't actually tracked those, but anyway, the point is it's an important kind of aspect of the issue that we're studying in this. If you're interested in machine learning, so what fairness wants to achieve is, I think, very well illustrated in this picture, where we wanted to ignore some irrelevant or protected attributes when we're making certain predictions. So to give you an example of point of failure, let's say we're trying to classify the hair color using images of faces. And so if your data contains this bias, this spurious correlation between this label, blonde hair, versus this gender attribute, female, you end up picking up on those kind of biased factor, which shouldn't have been, because you don't really need to see this attribute to be able to predict the label with high accuracy, right? So to see some of the common factors that cause bias in machine learning model, here I'm summarizing a few. The very first one is spurious correlation, which is exactly what the example showed earlier. So some other common example could be, associate man with computer programmers, and then the second common cause could be due to sample size disparity, especially your training data that has some minority group, which, in terms of population that is much less than those majority group, it's very likely that your model would be in favor or try to capture this dominant signals from this majority group. And there's a third cause, which is proxies. So let's say even if we can remove some of the sensitive attributes such as race, gender during this training process, it's possible that there might be some features that are implicitly kind of associated or used as proxies for those sensitive attributes, such as the neighborhood that you live, right? So those could, if not being used carefully, could also cause undesirable kind of unfairness. And so to define this notion more formally, we have this definition called statistical parity group fairness, which essentially tries to say we want to equalize two groups, S and T, at the levels of outcomes. So to translate this into, probability language, essentially we're trying to say the probability of having outcome O conditioned on this group of S is equal to this probability of the same outcome conditioned on the other group T. So in other words, to explain in a kind of example here, the fraction of people in this group getting a job offers is in the other group. So that's the plain language explanation. So this is a recent paper came out from Percy's group at Stanford that tries to address some of those group robustness issues. So to review this methodology at a very high level, you can think of this this ERM, empirical risk minimization, is the classic way to to minimize your loss at a population level. So basically, you're taking this expectation over all the samples drawn uniformly from your distribution P, and then minimize the loss on average. But this, remember, if you have some minority group that is kind of less represented, you're likely to fit this ERM model that produce very low accuracy on these groups. So to fix those issues, the author essentially proposed this technique, GDRO training objective, which is to minimize this empirical risk with respect to this worst group, right? So in your optimization, you wanted to take this G out from all those possible groups, and then calculate, which group does kind of badly, and then minimize this loss with respect to that group. So to see how this isn't, again, you've seen this example already, and this is, for example, your training example might have a lot of birds, let's say, with label water bird with water background, and similarly with land bird with land background. And so your model would kind of perform badly on those water birds that have land background. And to fix those issues, this is how GDRO actually works. On this left side, you can see that when you're measuring in terms of average accuracy, right, you can see this ERM model or DRO model is actually all working pretty well across the board. But if you have zoomed into some of these underrepresented group, let's say worst group, you can see ERM is actually doing terribly, reaching this train and test accuracy on water birds data set around 35.7%. This is train, and test is even lower. So after optimizing using this new technique called GDRO, this is able to improve your worst group, which is the underrepresented group, substantially to the test time performance 84.6. And I also want to, just to call out that, group fairness isn't always desirable, and it's really task dependent. So in this particular example that I'm showing you guys here, let's say malicious vendor wants to sell a high-fee exclusive credit card only to people who have purple skin, not people with green skin, right? So it's a very targeted kind of group. And if you target 500 high-income people with both skin colors, yes, you are achieving this group fairness with respect to both groups, but it doesn't really kind of fit within this application need here. And in addition to this group fairness notion, I also want to point out there, you probably will see some literature that talks about individual fairness, which in a simpler notion, what this tries to achieve is to say, treat similar individuals similarly. So effectively similar, let's say similar people should have, should produce similar outcomes in your machine learning model. And to formalize this notion a bit, we can use mapping M that takes an input and then maps this input to some outcome space, delta here. And if we have some certain, distance functions that could measure this closeness in this original space, let's say D, right? This is the function that measures how close two individuals are, X and X dot. And then ideally, if this model is achieving individual fairness, this outcome, M of X, the distance between these two outcomes should also be, sufficiently close. So that's, one way to define this. Okay, so that's all the important bits that I wanted to provide in this overview lecture, and I just wanted to summarize what we have gone through today. It's really a lot of stuff that we covered. So to refresh, we first talk about this out of distribution reliability. Thanks for the question. Let me get to that. So we first talk about out of distribution reliability, and in particular, we've seen several approaches that tries to defend against those OD examples for pre-trained models, such as MSP, Odin, Mahalanobis, and I also talk about energy-based approach. And there's another line of approach that retrain or fine-tune this network to achieve even better performance, which we will see in the next paper presentation. And the second subtopic we've seen today is adversarial robustness. And in particular, we've talked about the generation, how to generate and defend against adversary examples. And then there are also some interesting conjectures we've looked at, try to explain why adversarial examples exist. And lastly, we look at fairness, which is also kind of a rising topic in this trustworthy machine learning literature. And I've talked about this causes of bias due to spurious correlation, the sample size disparity or proxies, and so on. And then there are different definitions of fairness, for example, group fairness, statistical parity that we've looked at, and also individual fairness. So that's, then, we've looked at one particular example in terms of training optimization techniques that is catered for this improving worst case performance. So that's all we have for today, and thank you for being here. And now I will And also my office hour is right after this lecture, so I will stick around, and then I will stop recording and to start addressing questions.